I'll start shortly. I'm just waiting for some more people to join up. If there aren't more people at 10 past, I'll get going at 10 past. Okay, cool. It is 10 past 10, so if there were any stragglers, they would have got up by now. So I'm going to get going. So this is workshop 4 of Python for data science. And the goal of this workshop is that we'll go over some last bits of the functionality in Numpy and just refresh on that, and then use that catch up from Numpy, and then go into pandas and explain some of the concepts in pandas, which is one of the main data science tools we're going to be using going forward. But first, I'm just going to cover some of the indexing and the array reshaping and broadcasting and those kind of things that exist in Numpy, and I'll explain what they are and how they work and why they matter to us. Okay, so back in workshop 3, when we were looking at Numpy arrays, okay, let me first make a file and then I can talk into a file. Oh. This is going to be workshop4.py. Cool. Import Numpy as Numpy, and that's it. So when we were speaking about Numpy arrays earlier, and we spoke about all the things that you can do with Numpy arrays and how they're faster, and we did some performance testing. The one reason we mentioned why this is because they're all not happening in Python anymore, but in C code running in the background. And running that pre-compiled statically typed code. And the statically type is the important bit here, because that means that if you've got an int in a NumPy array, it's going to stay int forever. It's not going to switch to a float. It can't. It is only int going to there. And that's part of what lends it its speed, because it doesn't have the overhead of having to deal with dynamic types. It's only one type. So let's just do an example of that. If in NumPy you go, and we just have an array, and we're going to use a range for this one. 1 and 10. Cool. So, is there. Yeah. So then if we look here in the console, of course. Sometimes you make a typo and then nothing works. Cool. So there we go. We're using a range, which all that does is it gives us a value between 1 and in this case 10, non-inclusive, it's exclusive. So you get 10 values from 1 to 9. Cool. And the reason we're going to do this is because the first thing that I'm going to just expand on a little bit and show some of the other things that are out there with it is indexing. So indexing refers to how you access the values inside of an array. And for me, while I'm busy here, create x2. And x2 is going to be numpy, but L in space. And what L in space is, it works very similar to a range. It also takes in the start and the stop. But what is different about L in space is it returns an array of floats. And the reason for that is that it's a lot more about the with a range, it's a lot more about your stepping, because you could step by a specific value. In our case, we're leaving it null. Where with L in space, it's more about having a start and stop that's specific, and then just the values inside change. So if I put 1, 10, and I want 10 of them as well. I put that up with we'll see we've got two, one from 1 to 9, and one from 1 to 10. And the one is also plus, you know, because there's a full stop there. Cool. So now we've got some things to work with. Now, the most basic way that we can do indexing with Numpy is the stock standard. So for all of these, I'm just going to put a print so we can actually see the value that we get back. So the most basic way that you can do indexing in Python is with 2 square brackets and then just the value of the index that you're going to be sampling at. That's just if you want to sample a single index. But with that same concept in mind, if I'm going to go sample -1, I'm just going to comment that out. So if on X, which is this 1 to 9, I sample 0, I'm expecting to find 1. But if I sample -1, then I'm expecting to find 9. So it's a reverse index based on, if I make that 2, it's going to be 8, and so forth and so on. So that's just a cool thing to be aware of, that you can reverse index. And another way that we kind of saw while we were doing our Boolean masks for the end of last workshop when we did statistics with our data that we pulled into a Numpy array. One of the things that we saw is that you could have an object that you define. In this case, I'm going to call it index, or just in for index. And it's simply going to be a normal array with a few values in it. So I'm just saying some random values 2, 4, and 5. And then you can, in your indexer, you can just pass this list in, and that list will then return its values. So let's just make this a little bit more clear what's happening here. Single index. And this one's going to be reverse index. So all I'm doing is I'm just adding some text into our print so it just reads a little bit cleaner. And this one is going to be our list of indexes. Cool. So I'm just going to clear this console and run that. There we get single index 1, reverse index 9, and then the values of 2, 4, and 5. In this case, 2, 4, 5. Match up. Yeah. Cool. So those are just some more ways that you can index. But now, when we're doing this list-based indexing for our finding the values inside of a Numpy array, there's something important to note, that the values that you get back, the structure of them, how many arrays and the layouts aren't based on the values itself inside of your array. It's all based on the indexing format that you give it. So in this case, I gave it a flat array and I got a flat array back. What you can do is, you can go and you can say index is equal to numpy dot array. And in this case, what I'm doing is I'm just creating a multi-dimensional array, just manually typing in the values just to quickly get some random values to sample on. Cool. So those values don't have any meaning or correlation or anything, they're just between 1 and 10 in this case. And this little, it's pretty much, if I have to them out, it's 2 rows and 2 columns of data. So it's a 2-dimensional array with 2 values inside of each. Cool. So then, right here, put this out. This would be multi-dimensional indexes. What that gives us back is it's just a simple object In this case, a Numpy array that I pass into my array to get it back. And oops. I have two little brackets on my slides. Yes, there we go. You don't like it. This is Python after all. Yeah. Cool, circle bracket. There we go. Sure. First, I'll leave out a bracket and I replace the bracket with the wrong kind of bracket. But there we go. So, what it is pretty much is it's array containing two arrays inside of it. So it's just a multi-dimensional, pretty much matrix. Then what we get back is our matrix of data in that format. And the indexes still correlate to our flat array over here, if that makes sense. Cool. Okay. So that's just the multi-dimensional index sampling that you can do. And then the next step that we're going to do is we're going to do some array slicing. So all the sampling we've been doing to this point have all been with the two square brackets index sampling. And the other option that we have for sampling is that you can use the colon. And what the colon does is you put it inside of your normal square bracket sampling. So if we're sampling on the collection X, in this case, then you say your start index, you put a colon, then where you want to stop index, another colon, and then the step in which you want to sample. Well, what makes this operator special is if you leave any one of these values out, then it will fill it in with a default value. And those default values correspond to, so there would be 0 for the start. It always starts the start at 0. Then the stop would be the size of the collection in this case. So if this has a size of 10, which it does, then it would be 10 in this case. And then the default value of step is always 1. So those are just explanatory values, not actual code. So let's see what this would look like if we wanted to use this special operator that works in this format, our slicing operator. It's called the slicing operator, or the subarray operator. It's both are valid terms. So if we wanted to just grab the first 5 of the values, what we would do is we would print. So we're doing it inside of our collection X, put our two square brackets. So we wanted to start at 0, we wanted to end at 5, and then the step is going to be 1. But we don't need to define the step because its default value is 1. So we can leave that out. And then because the default value of start is also 0, we can also remove that. So all that's left is inside this two square brackets, we've got a colon and a 5. And that uses this format to then only print out the first 5 elements. So let's do that. First 5. Cool. So then the inverse of the first 5 elements, oops. We wanted to do the inverse of the first 5 elements. It would be as simple as putting the 5 on the other side of the colon. So then it would start at the start at 5. It would stop at the size of the collection, which is the end. So we would stop midway and end at the end, cool. And then we would do it at a step of 1, which is also fine. Cool. Let's check now. Let's just clear this console. and then run our script. And what we get is, it is the first 5, and it is the last, in this case 4, because our collection contains, let's actually check what our collection contains. Shit. Nine values, because a range is exclusive of the 10. So it would contain 9 values. So the 4 there is correct. Awesome. Yeah, so you would get 4 values in your second 5 because the 10 is exclusive. So ln space is inclusive of your start and your end, and a range is exclusive of the end value but inclusive of the first value. So it would contain 1 but not 10. So then if you wanted collection X to contain 10 elements, you either have to shift up this to 11 or on the first one to 0. I like 0 indexing, so I'm just going to make the first one 0, but that's, it doesn't matter, it's example data just to illustrate how the sampling would work using these new sampling concepts. So now we've got these subarrays that it's printing out. And we're currently just using the start and the end. So we can use the start and the end together. Obviously, that's the next one. So if we were to just cut out the middle, and you start at 4 and end at 7, that's the middle values. Middle values. Oops. Cool. And then if we wanted every other one, so in this case, we're going to use our step for the first time. So if we look at this, where we're using the slicing or the subarray syntax, you see there's 2. So all of these so far only have been using 1. But if we only want to step in a scale of 2 and select every second one and return that, what we would do is we'll put 2 columns and then 2. And then that will give us every second value. Cool. Let's have a look. There we go. Every second value. And now, of course, you can combo any of these. These are just to illustrate the different aspect of this. If you wanted to start at the second one and only do every second value, then you put a 2 there. Or if you wanted to take from 4 to 7 but only counted every second one, then you put a 2 there. Yeah, you can use the full set of them or none of them, or some of them it's just another operator that we have access to that is fairly nice. So another really cool thing about these array slicing or subarray syntax is with this step, we've got a similar thing that we have here with this reverse index. So if the reverse index, if you've got -1, it's the last value. If you've got -2, it's the second value. So if you were to step through an array, minusing 1 every time, you would go from the beginning to the end. So if you wanted to inverse a Numpy array really quickly, the quickest and easiest way to do it is surprisingly taking the collection, just putting 2 columns and then -1. And then it would inverse your array and give you the inverse values of your Numpy array, which is really cool. There we go. So then it starts at 9 and goes down to 0, whereas at the beginning it's 0 to 9. Cool. So that's just a quick and easy how to use a subarray. So now the subarray there's actually a bit more to it than, because what it looks like here is as if we're just copying the data in the array and returning it as values. And it absolutely looks like that. But what Numpy is doing behind the scenes, it's not creating duplicates of your variables for you and putting them in your RAM again for each time you do something. So what it does is it creates something called the view internally inside of Numpy's magical black box that does things inside for us. What Numpy does is it creates a view. So this collection of ours, each one of these, if we were to store them in a variable and change one of the values inside of it, it would change the original one's value inside of it. So that sounds fairly weird, and the data we've got is not quite nice to illustrate that. So what I'm going to do is I'm just going to make a new file and then put some more test data in there, and then we can do that example and see what I mean with it creates a view, not a clone of the data. So I'm just making a new file, and I'm going to make quite a few files during today's thing, and my naming convention for them is literally just going to be workshop 4, workshop 4B, and so forth and so more, because it's a bit more example based and just getting some of the more advanced concepts of what we can do with what we already learned. For the inverse, you only got up to 1. So if you look at where you define x, and it's equal to MPA range minus 0 to 10. If yours is 1 to 10, then you would only go down to 1. Yeah, it's simply the inclusive and exclusive on. So what a range does is it returns a value for each honest step, and then based on from where to where. Cool. Yeah, sorry if I lost you there. Feel free to yell and I will reiterate anything that you would like, because you are here. Okay, so in my new file called workshop 4B, we're going to do numpy as np, just once again, and then we're just going to use access variable name again. We're going to use numpy, and then we're going to arrange again. But where it's coming in to be a bit different this time is I'm only going to put in 12. That's it. And then after that, I'm going to use a new function that I'll explain a bit later on. I'm just going to use it to get the data and then describe how it works in functions and how we're going to be using it. So then reshape. And inside of reshape, I put 2 more brackets. And then 3, 4. Cool. So basically, no, don't do that. Cool. So basically, what's happening in this new file of ours, we're just importing numpy. With numpy creating a new array that has 12 values inside of it. One of the ways you can call array range is just putting the amount of values you want in there, and it will count up from 0 to that point. There's a few different ways. It's just an alternative way of calling the same function, and then it behaves in a specific set way. And then reshape, I will explain just now when we get there. But what it effectively returns for us is, if you see here we've got 3 arrays basically. We've got 3 rows and 4 columns. So in the reshape, there's a 3 and a 4, and the 3 is the rows and the 4 is the columns. So I will explain in detail how that works just now. But the reason we wanted 3 rows and 3 columns is we wanted to demo how the sampling of using a substring or a slicing syntax works versus actually copying the data, how it links back to it. So that view I spoke of is easily seen if we go, I'm just making a new variable, in this case I'm calling it X view, you can call it anything you like. And then what's going to be inside of it is our data collection. And because it's now a multi-dimensional array, what I want to do is I want to, in this specific case, I want to sample two values, and then we use a colon again and two values. So if we look here, where we have a start and a stop. So because I only have one colon and then a stop value, it's going to start at 0 and then do 2, and then it's going to start at 0 and then do 2. So X view gets set equal to pretty much. Instead of explaining it, I can just print it actually. That's why I made it. Cool. So basically, that's 0, 1, and the 4, 5. I sampled them into our X view as a view of the data inside of X itself. So now with X view, if I, for example, go and say, I'm going to change the value inside of X view, and because it's still an array, you still have to sample the specific data element inside of it that I want to change. So I'm just going to do 0, 0. So that's the one on the top left, which in this case should be 0. Will be 0, is 0. We can set it to, let's pick a random number. So it goes up to 11, so I'm going to say 12. So then, if we print this X view, what we're expecting is that the first value inside of X view is now going to be 12. But then also, because using the substring sampling technique that we're using here, and sampling multiple values after each other to make us a new array collection inside of our new variable. And this view just refers back to our main data without copying it. If we print our main data again, what we'll see is that the first value in it is going to now also be changed. So let's clear the console, clarity. When I run it, here we see. Initially, what we're doing is we're creating this object. Then we're sampling out the first 4 values there into X view. Then we change the value to 12. And here you can see when we put X view again, the value is 12. And then X also, the value is 12 again. So everything still refers to each other, and it effectively is a very light operation because it just keeps referring to things instead of creating new copies of your data in your RAM the whole time. So this is fairly useful, for example, when we were in workshop 3, when we did our Boolean masks at the end of the workshop. We went and said, this section is summer. And you can then, you could do arrangements and values and stuff on summer with that Boolean mask. But using the Boolean mask, you can sample it into a variable as well. And then you've got all the values from summer in a specific time step or specific value step or anything like that. You can sample into variables and then do calculations in that second. So it's a very useful default behavior for these slicing or substring subarray processes to do, which is fairly nice. But sometimes you do want to copy the data. So if I change the value in here, I don't want it to affect all the way back to my main data. So I'm just going to show you how to do that. When you initially sample, so instead of X view, I'm going to call it X copy. So when you initially sample your data out of your collection, you can still do it the exact same way. So we still want the top 4 values pretty much. So that is :2, :2. So the exact same sampling as we're using for the X view. But then you go dot copy. And you put your 2 brackets because it's a function call. And done. Now X copy any data you change in here does not affect any of your other data, it's all separate. So with this views, if I, for example, sampled the first 4 data into XView at the moment, but then I create another variable and I sample a later 4 that includes some of the data in XView already. So if I make a XView 2 and its other data that also includes some of the data in XView would also then update and change. It all refers back to each other and back and forth, which is a fairly convenient behavior if you want to filter down specific bits of your data and then work with that, and then zoom out again to a greater perspective of your data and back and forth like that. Okay, so that is doing sampling with your slicing or your Subarray. Any problems, questions, queries so far? But where would you want to use copy? So say, for example, that you've got you're doing an experiment, and you did your experiment 10 times. And for these 10 times, there was one of them that you know for a fact something went bad. So the data changed in a specific way. So then what you can do is you can actually copy that specific bit of data and specific bits of that data even. And then you can use that data as a Boolean mask on the rest of your data to see if any of those same behaviors happen anywhere else in your data. So then that's just a quick example I was able to come up with of where you would want to keep it because you know it's not going to change. Or you would then, for example, increase it by tenfold, but you don't want your original data to change, but you want your masking data to change, basically. So it's whenever you want to, yeah, that's where I have used it in the past. It's probably a lot further ways that I'm not immediately coming up with, but yeah, there are some rare times. Yes, generally it's nice to filter. Okay, cool. So then I earlier quickly used Reshape and just kind of moved on. So Reshape is the next thing that we're covering. And what Reshape is pretty much about is oftentimes that you get data in a specific format or collection or something, then you need to manipulate it a little bit to get it in the format that you want it or format that you need it. And the easiest way to do that is to use Reshape. The main thing about Reshape is it's so generic and nice and friendly, but I know for a fact there is 12 elements, and if I've got 3 rows and 4 values inside of each row, that makes up 12. If they're not the same, then you get some weird mapping and things go a bit bad, which is not something one wants. So Reshape is a very nice, easy to use, but yeah, just be careful with Reshape. And the other thing about Reshape is that Reshape does do the same exact thing as our substring or our array slicing, whatever you want to call it. It's the same thing. It makes a view of the original data. So it saves a lot on memory by not remapping the data inside of the memory, but inside of Numpy just going, okay, refer to that data now as if it exists in this kind of format, instead of linearly, which is nice and versatile and friendly, right? Which is cool. Cool. So now we're getting to some interesting things. The next one that we're doing is I want to explain what broadcasting arrays are. So the first example we did in workshop 3 was working with a reciprocal, and we talked about, let me actually I'm making yet another file. As I mentioned, I'm going to make a few. This one is called Workshop 4. Let's see. So I'm just making files for the sake of keeping my screen clean. You don't have to make a bunch of files. You can do it all in one file, comment everything out, do whatever you feel like. It's just, I like keeping a nice clean screen, and I want to keep the files as backups because I'm uploading them to the Git where my notes are as well. So you can see the project files that I used for the workshop. Cool. Import Numpy and Numpy. Cool. Cool, so we got our Numpy. 1 second. There you are. Just gonna copy this little thing. Cool. So this is that reciprocal function we used in last workshop, and inside of it, it has a for loop, and it does for each element inside of it. But then what we ended up doing, because we're using Numpy now, we didn't have to do that anymore. We could simply go 1.0 divided by, and then our collection of data, instead of having to do all of the other things. So I'm just gonna make a collection of data. X equal to numpy dot arange 0,10. I'll just give you 10 elements. So instead of feeding x inside of this values and having it run through, we would just be able to go print that, right? And Numpy would take care of all of it for us using this generic function. And what it's doing is it's taking one single scalar value, a single value, and multiplying it into an array. So now we get back to the array broadcasting that we were talking about. What array broadcasting is at the end of the day is a bit of code inside of Numpy that allows us to effectively perform these special ufuncs, these special sets of functionalities with specific behaviors that are statically baked into Numpy files on different sized arrays. In this case, what we're effectively doing is we're treating this as a array with one element in it, and this is an array with 10 elements in it. And then what it does in the background with the broadcasting, it goes, okay, so there is 1 point, and then it does it like that. Whoops, you copied too fast. Okay, that is not 10 times, but we're going to pretend it's 10 times, because apparently I can't that one button at a time. So it's effectively doing that because this x is equivalent to 1, 2, 3, 4, all the way up to the 10, right? So it's effectively doing that and then putting it equal to a new list that's actually this one, that value, this one, that value. But what broadcasting does in the background is it uses, once again, those views that we talked about when we were doing the reshapes and the subarrays and all of that. It does some view magic in the background. So it's not making new copies. It's just simply referring to the same value for the amount of times that it needs. So what I'm actually going to do with this file, that was just all to illustrate as I'm talking. What I'm going to do with this file is some really awesome smart people went and made a Python book that they made, what do you call them? Appendixes and figures, figures, that's the word. They made figures for that illustrate this concept really well. Then they wrote these figures inside of Python. So on my notes, there's a broadcasting arrays element that is blue. That's where I copied this link from just now, but I'm posting it in the chat as well. So that link, if you go to that link, you will see that there's a broadcasting and then a bunch of code. And that's pretty much the whole figure 3. And I'm going to copy all of that. And then I'm going to just paste that into the script. And then I'll explain why we're doing this process. Cool. So I've copied the whole figure 3, just not the images and stuff, so just the code that goes into figure 3. And as you can see here at the top, it's using Numpy and matplotlib as polyplot, and you just call it PLT. Same as we did in workshop 3, we're using exactly the same things. And then if we go to the bottom, we just have to quickly rename what it saves it to. So we're just going to move everything so it says fig, let's save fig, broadcasting.png. Save that file. Oh, that's fine. I'm just running through it to show you what it's going to do, and then you can do it. And then once yours work, I will continue from there. So then if I run this, what it did is it ended up making this image. So this image is the result of all of this code running, all of this Python just doing its little script. And at the end, saving out that figure. And then we get this image that describes to us how broadcasting works. Cool. I will let you quickly do that, and I'll have a sip of tea. Then let me know when you managed to complete that and put the image in there. Are you managing again? Awesome. So it's gonna make this image. Just remember right at the bottom of this thing where it says fig.savefig, just remove the beginning bits of that because we're not building the whole handbook, we're just building the specific figure that was relevant to us. Then you get this image inside the same folder where the script is. So what this image illustrates for us, if we look here where it says mp.arange3.+5, and that's so now that we've run this code and it's made this image, I'm gonna just take all this code away because I don't need it anymore. You're welcome to just save that file or whatever you feel like. It does not matter. I just don't need. Cool. So what it's illustrating here with this image So if I type this code out quickly, np.arrange 3 plus 5. 3 plus 5. So when you're running this code, you've got an array of 3 values plus 5. So you've got 0, 1, 2 inside of your array, and 5, 5, 5, or just a single scalar value of 5. And it uses that view magic in the background to make your other 2 5s, as you can see, it's starting to grayed out, to make a virtual completed version of the array for you. And then at the end of the day, you get 5 plus the first one, 5 plus the second one, 5 plus the third one. And that's how those vectorized, much faster, running in the C in the background functions that we've been using in Numpy, that's how they work at the back of everything. That's the thing that makes them work. And that's pretty cool. So there are pretty much 3 ways that it can go about doing this. If you've got one that is significantly smaller, it will complete it to the right. If you've got one that is the same length, but not the same width, it's got the same amount of columns, but not the amount of rows, it will duplicate its columns down into its rows. I might completely throw columns and rows the wrong way around. I do apologize if I do that. That is my inaptitude with columns and rows. I always confuse them. And then what this one illustrates is if there's at least one of them that lines up, but they're the other way around, then it can still propagate through and do them. So those are the 3 conditions that will make broadcasting in Numpy work. But if you, for example, have one that has 4 long and another one that's 3 down, then it won't run. It will throw you an error that it's a mismatch. So just keep those 3 rules in mind, and that's a nice helpful reference image. But as you probably noticed, we've been using broadcasting in the background. We just were not aware that we're using it. So now that you know how it works, if you don't, please yell. But now that you know how it works, you can see problems ahead or avoid them because you understand the backing of what you're using. Cool. So that's broadcasting in Numpy arrays. And you can do a lot with these broadcasting kind of features. So in statistics, if you were to get the center of your data or to spot where a certain group of data is more prevalent, or if you're plotting a flow map, something like that, then all of this becomes a part of it, and you use it intrinsically inside of it. You just don't necessarily always notice. If you are interested in doing something like a flow map, optionally on the side, if you check in my notes, there is a link under the broadcasting, I believe it's the here one, that is an example of that you can do on the side extra. Cool. And then the next step. So the last Numpy thing that we're going to do before we go on into pandas is called Numpy's structured arrays. So Numpy structured arrays are probably the most powerful thing that they've got, but also the weirdest placed kind of feature. So what the structured arrays allow you to do is that you can have very efficient, very specifically organized in memory stored values that follow the Numpy principles, such as that they are heterogeneous and you can't change them after the fact. The type stack, that's the word I was looking for. So the example that I'm going to use to illustrate a NumPy structured array is I'm going to bring back that creature thing of ours that we did for the first 2 workshops. I'm going to use that as a basis just to have a bit of data to play with as a concept. So what we ended up having is, if we say we've got 3 variables, and let me just import NumPy at the top. We've got NumPy. Yes. Okay. So we've got 3 variables that's lists, one with a string, one with ints, and one with floats, right? And one's the names, the ages, and the weights. Simple. So what we want to do is we want to store these efficiently inside of a NumPy structure. Because as we've seen with NumPy, if we want to do calculations over a vast collection of things, it's significantly more efficient to use NumPy. So let's say we're going to have a large amount of them and we decide that we want to use NumPy. Sorry, I just found the problem in my notes that I updated. Cool. I'm updating my notes. Cool. So now we've got these 3 separate stock standard lists. Generally, what we do if we create a NumPy array is what I've especially been doing today in this workshop is I've been going dot, and then you can go arrange, or you can go L in space, or any of that. But there's also the ones and the zeros, and there's a large list of these different things that NumPy provides to you to allow you to just quickly create your data structures and give them default data effectively before you then write in your own data or load from file or whatever you want. It's just to set up your structures. So in this case, I'm going to use the zeros because I just want an empty structure. And what we'd usually do is we'd end up with something like that. And now we create our thing with our ints or our floats or whatever, and we'd have our values, and simple as that. But what it does in the background that we don't always pick up is that it's got the optional parameter. So the optional parameters are ones with preset types. So in this case, the D type there is the parameter that is in question, and it's a float. So by default, if you were to create an array with NumPy zeros, it would create you a float array, and that would be a float, so that would be a float for always. For our specific use case, we want to create a structured array that can contain our names, our ages, and our weights. So we want to create almost a new data format for our structured array. And that's absolutely what structured arrays are for. So the way you will, not to say the way, one of the ways that you can define your structured array types in NumPy is you can define a dictionary where you just lay them out. And that's my preferred way. There are a whole host of different ones. If you find one that you like, they are functionally equivalent. It's purely a syntactic choice how you define them. So my way that I prefer to do it is I go data format. It's just a variable, and inside of that variable, I have my dictionary. So what you do to define the format for a structured array is this D format, D type variable. I'm going to set equal to my data format variable, and then I will populate the data format. So what the data format consists of is you've got the names, and then you've got the formats of each one of the arrays that's inside of this data format. So we start with names in our case. So we say names. As it's a dictionary, you just do it the normal dictionary way that we've learned in Python. So the first name of our 3 arrays is name. Put in name. The second one is age. And then the third one is weight. So weight. Cool. So that is the I'm missing brackets for that. Is cool. That is the names. So now the next step is we want to define the formats that each one of these arrays that's inside of our data format is. And you just do them at the same index that you do the index of the name. Cool. So we say formats. There we go. Formats, and that is once again. And then there's a few different ways that you can refer to this, but you now have to define the format that you want this array to be in. So our names, we obviously want to be strings. And you can do it by using a shorthand, or you can do it by straight up defining them. So if you go to Numpy and you say str, and I believe there's an underscore. Yes, underscore. That is the Numpy string format. And then the next one, we want to be int for our age. So if we want to have a int, we go numpy dot int, and then there's a few different options. In our case, int 32 is way more than enough. And then the next one is numpy dot, and then the weight is a float. So float is floating point is 64, I believe. Yes, that makes sense. Because it's 8 bytes to 64 bits. Yes. Cool. There we go. So now I've got a structured array X that has a bunch of zeros in it, and it has the data format that we provided for it. So let's see if we did all of this correctly, and just straight up print X. And also, because we defined the custom data format and we know that it is a structured array, we know that inside of it that we can do the deep type. Cool. So we're on my console. On my console and run this. Cool. There we can see that we've got a bunch of zeros in there. Oops. We've got a bunch of zeros in the x1. So it prints x, which gives us the empty string, the empty float, and the empty int. Which is cool. That is cool. So in this case, I prefer for the float to just use the shorthand because it makes more sense to me, which is F8. So it's a float and it's 8 bytes with 64 bits. Cool. And then for the int, my personal preference is also to use the I4 because it's an int and it's 4 bytes, that's 16 bits. It's just also a little bit smaller, not that it makes any difference on the size, it's just my personal preference. I just thought I'd show you a few different ones. So now that we've got our structured array, we want to assign some values into it. So as we see here, it has a name, an age, and a weight, that each are in the right types that we need them for. So what we can do is we can literally go and in our X, which is our data variable in this case, and we want to set the name array inside of the structured array collection. So what we do is we go name. Same she would refer to a dictionary or a normal index that's usually a number. You would just put in the name, and then you say that's going to be equal to this list here of name. Cool. And then you just do the same thing for the other ones, which is age and weight. We check out our collection. That what we end up with is cool. And then we go here, name. That is interesting. Sorry, I am having an awkward moment where I am copying my code from my notes and they're doing different things. And now then, okay, cool. So I ended up replacing these out with my personal reference format. And as it turns out, you can only use one type in a complete sentence. So that one that was string, I replaced with a U10. And the reason for that is it's the Unicode string, and then the 10 limits it to 10 characters. And that's just why that is that. Then if we look down here, when we print X, we see that we've got our cat, our mouse, our fluffy, and our whiskers, which is all of those. And then they've got the linked to them at the right index, age, and weight as well. So then if you call just the name, you just get a list of all the names back. And then with this structured array in Numpy, you can do all the same indexing and full masks and all of those different bits of functionality that we covered in the previous workshops as well. So, let's do a quick example. If we were gonna get, let me print first. So what we want is we want to get the name. So we want to get the name, but we only want to get the names of, let's say, creatures that weigh more than, let's say, 15 units. So then what you would do is you would put another two conditional brackets before it. And this is where you then define a Boolean mask. So in this case, it would still be X. And then we're talking about the weight in question. And then the weight. Cool, spelling's exactly the same. And then it's less than 15. Cool. And then I'm just going to add my print value in. So only cat and mouse weigh less than 15, because I have my bracket the other way around. That's it. Cool. Only Fluffy and Whiskers weigh more than 15. Cool. So you can do all your normal Boolean masks, all your sampling, and with these structured arrays, you can then also go and you can do your subarrays, your array splittings, all of that. And they would also do the whole view separation instead of cloning your data. So yeah, all of these different things link back together in a nice, neat package. And that package is the basics of Numpy. So we've now officially gone through all the basic bits and pieces that you'll encounter inside of Numpy and how to use them quick and easily with examples. We will do a bit more intense things than that in one of the future workshops. So one of the things going forward with these workshops that I want to put in is the original in-person workshop was supposed to have a component where you would be able to complete the specific laid out project for the workshop by yourself and then upload it to a Git that would then be able to be reviewed if you would like to. And that also allows you to have your process reviewed and get feedback on things that is noticed in your code that might be a problem and all those kind of things. So I will make, as I've mentioned today a few times, there is some optional supplemental links in between my notes. I'll make those more, and I will give a overarching project for the next workshop as well. So that's where I am leaning with that as a heads up. Cool. So that is all of Numpy. The next and last bit of this workshop that I want to cover is pandas. So pandas we have used before. We actually used it in workshop 3 to pull out the specific rainfall data that we used and put it into our NumPy array for us. And that just worked back and forth really nicely. And the reason for that is that pandas is actually built on top of NumPy. And pandas and the Panda data view and data frame objects as they exist are very much simply structured arrays with a lot of functionality and a lot of human-friendly features attached to them. So if you look at these, all of these values are indexed to an index value. What makes a Panda data view is a Panda data view doesn't have limited index to a number, but you can index it to a value, any value that you'd like, and it also has index objects. So I'm going to jump right into it with an example as well. So I'm going to make a new file. Oops, file. And that's going to be cd. Cool. So I've got A, B, C, and then these are your cool. Then inside workshop D, then I'm going to clear the console. We're now going to still use NumPy because pandas are based on NumPy. We'll be using a lot of the NumPy functionalities to make it work at the end of the day, because NumPy is a really nice bundle of functionality. Cool. And then we need to import pandas. Pandas is just pandas. And then also similar to NumPy has somewhat of a standard way of referring to it, and that is with UD. Seeing some interesting things in my notes here. I'll fix it after. Let's go. Cool. So we've imported NumPy, we've imported pandas, and now we want to start making pandas. So pandas has two things that are both similar to stuff we've used before. And the first one of those is a panda concept called a series. What a series is it's if you were to draw an analogy between what we just used in Numpy and what we're going to be using in pandas, it's very much just an array with a set value, and it is a static value that can't change as well. But the difference is, as we mentioned earlier, that pandas aren't necessarily just indexed by numbers. They can be indexed by anything you want to. So let's just have a look at how these series looks and how we define them. So make a variable and call this data, because I've called too many variables x today. And we go pandas dot series, and then we need to give it some starter values. And the starter values I'm going to do for this one is I'm just going to use something we've been using all day. Numpy dot arange. I'm just going to say 5. Give me 5 values. Cool. Then what we want to have a look at is what this data looks like. Pandas has a different data layout. So in particular, what we want to see is we want to see what the values in the indexes look like, and then what happens when you change them. So we go data index, and we go data values. Oh, run that. There we go. So it is at the moment it's very much indexed 1 to 4, the values 1 to 4 to indexes of 1 to 4. And it will, because we only supplied it with data, no index, which means it automatically defined itself an index. And then it was just the values 1 to 4. We could have put random in there and we've put random values, but that's not, that's just an example. Cool. So now let's look at what a more dynamic one looks like. And actually define one. Cool. So if we put a string in there, like a list in there, just the 2 square brackets defines a list in Python. We go 1, 5, 6, 7, 4. And that's our values. Those can be anything. And then index is the name of the property inside of the function series. So a lot of these modules and packages that we're importing, including Numpy, often have a lot of optional parameters that you can call on all of their functions and all their constructors. As we're calling a series constructor here, one of them that we do want to call in this case is we just want to provide it with an index to use so it doesn't generate one from integers. So then that's also just a list. The values inside of it, I'm going to say A, and then B, and then C, So we've got 4 values, and then we provided with 4 indexes. We run our code again. What we end up with is we see here that it mapped A to 1 B in the same index layer. So what this effectively means is now at any point you can go and say data and then put in A. And that is very much how it looks in a dictionary, right? So we've got almost a dictionary where we can have any index that we want, but our data type is static. And it's only one-dimensional. And that's what a series is. There are a few more things behind the hood with a series. So when we called the index earlier, right at the beginning, when we simply use the A range. If you see here in my console, you'll see it has a range index start 0, stop 5, and then step 1, which should probably sound familiar to the Subarray values, because it's the same values that has a start, stop, step. And the reason they are so very similar is because your series object, it has a special thing from pandas called the indexer that it uses to speed it up in the background, and we'll actually create some indexes and use them in the next workshop. For now, you just need to know that they exist and they are fantastic, and that it makes it a lot faster. So similar to where there are some cases where you want to run Numpy on an array of data, there are cases that you want to start using pandas when you've got a lot of data and you want to do generic processing on them. Yeah. Sorry, I just had to mute my mic there for a second while other people create it fast. Cool. So that is a series. Now, one of the other things you can do with a series is similar to a dictionary, is you can just provide it with values. So what we're going to do is I'm going to create a new series and then expand from there into turning our series into a data frame. Let's do that. I'm going to be copying, for sake of expediency, I'm going to be copying the data from my notes. If you need the link, let me know and I will give you the link. So it's just quite a bit to type out. Cool. So then I'm just going to place the explanation code with just this. And all this is it's pretty much the, it's a dictionary consisting of states or cities. I think those are states. And then the population numbers inside of each of them. And then I define a series that takes in this dictionary and I put it into a variable. Cool. So when I run this function, you get a nice data structure, and it's all in 64s because they contain the big numbers. Cool. So now, if we want to take the total area that each one of those same states take up, there's another data collection, and we're also just going to put that into a series. Cool. So now effectively what we have is so we've got two dictionaries, and in this case they have exactly the same keys, which means that if we have two series, they'll have the same indexes. They won't have missing indexes between each other. And then we've got our population, and we've got our area. Each is a series. And then we can go, and we can create a new variable called states. So we're going to set equal to a pandas data frame. And then once again, this is just one way to create the data frame. We've already done another one where we did rainfall data, and I'll refer to that example after this one again. It's just I'm doing it for this example. Cool. So then what you put into your data frame, because it already now has a not that. We already have two series, this with data inside of them, and they have the same keys. What we can provide to pandas, and then it will populate us a nice little grid, is all we have to do is we have to give it the keys associated with each one of these series. So for the population one, its key is going to be population. So I make a new object, so the two curly brackets, and then inside of this object or dictionary, in this case, because of the things inside of it would be functionally equivalent. So in this case, it's the population. Cool. And what that population is then equal to, with your colon, is the population series that you have. And you don't refer to it with quotation marks, because then it would see it as a string instead of this variable. Cool. Then it's just comma, then it's the other key, and the other key would be area. That's area. And then the value associated with that after the two, that's the column, is area as well. Cool. So now I've got a data frame that we provide two keys to and two series to. And these series share the same keys or indexes. They're called indexes with pandas. They share the same indexes with different values. So if we go and we print it, that's fine. What data frame has done is it's pretty much combined our different data for us. Done. I'm just going to, for sake of not filling up the console, comment out the two other prints because we are aware that those work. So we don't need to see them again. I'm going to just clear this. Cool. And then run now. Cool. So now what we've got is we've almost got a small database object that contains a list of keys, indexes that are states, and two other indexes that we also provided. But those would be our rows, and these are columns, or the other way around. But you've got a data frame object, which was cognizant of all of these. So Pandas is smart enough that if you were to leave out some of those keys in some of them, then it would just put a NaN value in for you, and it would say the key didn't exist. I am sorry, I couldn't make that happen, which is fairly cool. So it is error safe, because oftentimes when you're working with large format data, there might be some discrepancies, or some data somewhere got corrupted, and then you end up with a problematic stance where you are lacking values, and then your normal database software would throw error, and then it would hang, and you couldn't throw your normal commands at it. But if you're handling all that data in something like a pandas object, then it would be more error tolerant for the person that generated the data, because they would know what they're looking for and be able to facilitate. Cool. So that is that kind of object. So the next thing is our series have indexes, and yeah, they're also called index. Are they called columns? Oh, they're called index. Yeah, all right, cool. So we've got our index, and then the other one I will columns. Cool. So data frame has indexes, which are down the side, and your different columns of data. And then if you call them, you get the list of them, and they are of the D type object. Because when you start working with your indexes, then you can refer to those objects and modify those objects in really interesting ways. Cool. I think that is all I wanted to show during this workshop. Confirm my notes, yes. Cool. Are there any questions, concerns, queries, things you would be interested in seeing, anything like that? Yes, please ask. Oh, okay, cool. So your question is in workshop 1, we ran the lines of code via shell, and we used the terminal, and now using the terminal in VS Code, and can highlight the differences and benefits and all that. So the main reason that I was using the console in the first workshop is during the first workshop and later on as well, but I made it clear that people are allowed, and if they want to use any text editor that they want. So if anyone chose to use a text editor that I wasn't familiar with or didn't have a built-in console, then they would have a problem where they sit, and if I just hit run in console or hit the nice button in Visual Studio Code, they wouldn't know what to do and wouldn't be able to run their code. So I did it through the PowerShell to allow everyone to do it, regardless of what platform they chose. But other than that, actually, if you look here, I just switched mine to PowerShell. I've been running in Python because it chose to, but you can just run it in PowerShell here, and this terminal is referring to the same terminal that exists on your computer. It is functionally the same thing. There are a few slight differences, but not really. They're all the same thing. And this button, all it does is it just runs my Python and the script that I'm currently open to. So it's just a convenience thing, and it's nice to work in a text editor that I know the bits and pieces of, but yeah, it was simply if someone chose to do it another way, they knew how to do it, and I wasn't leaving anyone behind for that. There's no inherent benefit from doing it other than this is easy. Cool. I hope that awesome. Yeah, no problem at all. I quite enjoy giving them. I hope they're informative and you come away knowing more than when you came in. That's the goal. Cool. Any other questions or queries or things you would like to see going forward? If not, then we are done. Yeah, so the next workshop is going all into the indexes and all that for pandas, and I've got 2 other data sets that I pulled from open source data that we can play with and do some things with. I just had to brush up on my own statistics because I realized that I am not too fresh on statistics. So during brushing up on my statistics, I also learned a lot of the different indexes, things that I have been using can go a lot further. And a lot of the things that I naturally would use, you guys don't necessarily know even yet. So in this workshop, I just focused on making sure you know all of the different ways that you can quickly get stuff. So I didn't use something and you guys are lost. As well as just had a slow introduction to pandas rather than going, bam, here's pandas, bam, here's indexes, let's go. Which I think worked out okay, because we got a lot of the more like what happens behind things. Well, I said a lot about the things that I don't know if it made any sense. I hope so. Yeah, which is good, because I've got a frame of reference when you look at something and go further with that. Cool. Awesome. Cool. Thank you very much for attending. This is the end of workshop 4. Workshop 5 will probably include a product that is finished on your own time. Cool. Cheers.